In this video, we will talk about how do we test if a given set of vectors is linearly independent or not. Okay, so to answer this, we want to recall something from our video last time when we introduced what linear independence was. Okay, so here was our definition of linearly independent. So remember that the vectors v1 up until vk are linearly independent if when we form this linear combination of them to equal 0, the only solution to this is the trivial solution, where all of the weights c1 up until ck equals 0. And when we describe this, we reworded this equation and put it in matrix form. So we put the vectors v1 up until vk as the columns in a matrix. And we said that, oh, in the context of a matrix, this homogeneous system should only have the solution where the vector x is the 0 vector. So when that happens, when that's the only solution, then the vectors v1 up until vk are linearly independent. Okay, so I want to write that down here. Okay, so I just realigned the page a little bit. Okay, so the vectors a1 up until ak are linearly independent if and only if when we form this matrix equation, so if we put those vectors as the columns in this matrix A, this homogeneous equation has a unique solution. So only one solution. And if it has a unique solution, well, we know that the 0 vector always works. So if we say it has a unique solution, that's got to be the only one. The only solution is where x is the 0 vector. Okay, so the vectors are linearly independent if and only if the equation ax equals 0, the only solution to that is where x equals 0. And we know that happens. We know that a system like this has a unique solution if and only if A has no free variables. And that is the key right there. That is the key fact that's going to let us check whether a set of vectors is independent or not. Another way to say this is, so i.e., in other words, there is a pivot in each column of A. So A is our coefficient matrix. It's not the whole augmented matrix, it's just the coefficient matrix. Okay, so let's box this. Okay, so I've gone ahead and boxed that key statement right there. So the way we're going to check if a given set of vectors is independent or not is check to see if there's a pivot in each column. And if there's a pivot in each column, then the vectors are linearly independent. So let's do an example. Let's test if the following set of vectors are linearly independent. And if they're not, so if they are dependent, then express what's called a linear dependence relationship among them. So we'll get into what that means if we see that our vectors are dependent. Okay, so I have these 3 vectors, and I want to test to see if they're linearly independent or dependent. So I put them as columns in a matrix. So I'll have -1, 2, 1 as my first row, 1, 1, 2 as my next row, and then 2, 0, 4 as the third row. Okay, so notice that I'm just forming the coefficient matrix here. I'm not doing the whole augmented matrix because I don't really care about what's on the other side, just what's happening in the coefficient matrix. I just need there to be pivots in each of the columns of the coefficient matrix. Okay, so now I want this guy, this -1, to be a pivot. So let's do row operations to make the things underneath that become 0. So let's add the first row to the second row and insert that into the second row. And then let's take 2 times the first row and add that to the third row and substitute that in for the third row. So if we do this, the first row stays the same as -1, 2, 1. The second row changes because I add the first row to it. So that'll give me 0, 3, 3. And then for the third row, I'm going to multiply the top row by 2. And if I did that, this would become a -2, this would become a 4, this would become a 2. And I add those green numbers to the numbers in the third row. So that would give me 0, 4, 6. So 0, 4, 6. Okay, so awesome. Alrighty, so at this point I can see that, oh, this -1, that's going to be a pivot. I can see that, oh, this 3 in the second row, that's going to be a pivot. So next I got to sort of zero out the thing that's underneath that 3. I got to zero out this 4. Well, one thing that I might notice is that everything in the second row is divisible by 3. So I'm going to scale the second row. Let's do 1/3 times the second row, and insert that into the second row. That's just going to make my next computation a little bit easier. So the first row stays the same. The third row stays the same. Keeping those the same, I'm just scaling row number 2. I'm multiplying everything in row number 2 by 1/3, and that gives me 0, 1, 1. Now that I've done that, it makes doing a computation with the next row easier. So to zero out that 4, let's do -4 times row 2 and add that to row 3 and substitute that in for row 3. Doing this, my first 2 rows stay the same. So I'll have -1, 2, 1. The next row is still 0, 1, 1. But the third row is now different. The third row is going to be 0, 0, and then I'll get -4 plus 6, which is 2. Alrighty, and at this point, we can see all of the pivots. So I'm boxing all of them. So these are the pivots. So for our purposes, what we're looking to see is if there's a pivot in each column or not. And at this point, we can see, yes, there is a pivot in each column. So since there is a pivot in each column, that means the column vectors are linearly independent. And that's what this question was asking. It was asking, are these vectors linearly independent or not? Now I know that they are, because there was a pivot in each column of my coefficient matrix. Okay, so let's do another example. Now what if I changed my set of vectors a little bit? Specifically, I'm going to keep the first 2 vectors the same, but the third vector I'm changing to 12, 3, -4. Okay, so just like before, just like in part A, we're going to put these vectors into a matrix, into a coefficient matrix, and I've gone ahead and I've row reduced this already. So I've row reduced this matrix already. And now I look to see, if each of the columns has a pivot. So this has a pivot, the next column has a pivot, but the third column does not. And that's what I had kind of accidentally previewed a little bit here. So not all the columns have pivots because the third column doesn't have a pivot. So as a result, the column vectors are linearly dependent in this example because not all of them have pivots. Okay. So because of that, it should be possible for us to form a linear combination of these 3 vectors where the weights are not all 0 that equals 0. So what do I mean by that? How do we do this? Well, let's write down the equation for each row in this simplified form. So the top row is x1 minus 2x3, and then what's on the other side of the equal sign? So what I'm doing here is I'm wondering when I augment this with 0, so when I put zeros on the other side of the augmented bar, what will the solution be? So the other side of my equal sign is going to be 0. So the next row is x2 plus 5x3 equals 0. Okay, and then the third row I don't need to bother writing because the third row would have said 0 equals 0. And then I isolate the pivot variables, which are x1, so x1 equals 2x3. x2 is a pivot because there was a pivot in the second column. So x2 equals -5x3. And then x3 is free. So I'm going to leave that how it is. Okay. So now I'm ready to write down my answer as a vector. Well, actually, let's go ahead and do that here. So as a vector, x equals, I can factor an x3 out of each of my entries. And the coefficients are going to be 2, -5, and 1. Okay. So now, if we take the entries of this vector, those are going to be the weights in the linear combination that I'm going to set up in my linear dependence relationship. So thus, we would take 2, because that's the first entry, times the first vector, negative 1, 1, 2. And then the next entry was negative 5. So negative 5 times the next column vector, which is 2, 1, 0. And then the next entry is 1. So I won't put any coefficient there. Let's assume that it's a 1. 1 times the third column vector, 12, 3, negative 4. And if you check this, if you work out what this is, it gives us 0, 0, 0. Okay, so this thing right here that we've just written out, this is what's called a linear dependence relationship. A linear dependence relationship. It's a way to write a linear combination of my vectors where not all the weights are 0. That gives me the 0 vector out. So one sort of natural question is, well, what happened to the x3 when we wrote this linear combination? And the answer to that is, the fact that the x3 here means that if I were to take any multiple of this vector, it should work as a solution. So instead of writing 2 and then the negative 5 and then technically there's a 1 here as the coefficients, I could have written any multiple of those. So I could have doubled all of these and done 4 and then negative 10 and then 2, and that also would have worked. So that's what the x3 means. But in this problem, it just wanted one linear dependence relation, and that's what we've done.